Ladies and gentlemen, welcome back to the workshop. It is fabulous to have you here because we're restoring my 1915 Massey power hammer, and in the last episode, absolutely nothing went to plan. We decided that the head that was screwed onto our piston absolutely needed replacing, so I took a big old chunk of metal and made a brand new one to replace it. We can't install it straight away because there is half a threaded hole on both sides of our piston rod that we will never be able to match up with the correct location on our piston head, so these holes need to be filled up with weld and turned back down, so welding. God, aluminium. What a joke of a metal. Oh my goodness. Oh, I'm switching last names. What an idiot, I bought two of the same rods. I choose you! That's crap, isn't it?
Yeah.
It's like cooking spaghetti.
You gotta prep the rods first.
Yeah, you gotta prep the rods. Check on these rods. Good.
Man, I like them al dente, but they look a bit stiff.
You think they need more time? Been a minute. Do you think we're going to need to tell people that we didn't actually boil the 7018 rods? So I did all that weld build-up with some 7018 rod. 7018 rod is a rod that's quite susceptible to there being any moisture, so I made sure to bake the moisture out of it, and I made sure to preheat the part to 200 degrees Celsius. We clean it out nice and good with the die grinder. A little bead at a time, peening in between is supposedly the way to avoid some cracking, and what I'm doing now is I'm effectively trying to make it cool down really slowly on the outside of the forge. One of my big concerns about doing this is we're putting heat into a part that may have a lot of stresses in it, which may mean that we end up with a warped piston, which would be really unfortunate. I tried to keep the heat kind of localized to this far end there. If I come out of this day with a bent rod, I'm gonna be really upset. Hot out the oven. That's the maximum depth it'll go. I think this is gonna be the biggest shaft I've ever had to deal with in the lathe.
It's a good job you said in the lathe.
Oh yeah, no, this is nothing otherwise.
Looks pretty good to me.
That's pretty nice. Spin it to 50. Now we'll see how that dial moves as we come up. Bum, 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 bum. You will see we're obviously not straight by 0.25 of a millimeter.
Time to get the big dog out, is it?
You know, yeah.
What?
Oh, Tabby! I really need to put a crane above this lathe. Oh, we're within 0.02 of an inch. Let's do this. There we go. I'm now connected to the lead screw. What we now have to do is get the tool to slot into that groove perfectly. I feed across until we are in the groove proper. Gotta be very careful so I don't crash, because I have to stop this carriage perfectly there. There we go. Now we're getting the technique. We no longer have a thread cutting tool. We're back in business, boys and girls. Woo, we're cutting now. Broke the tool again. I felt that I was not quite engaged on the lead screw, and so I then bailed. But I think we might be able to try a test fit, so it's perfect timing. As you can see, that's our welded area that now has threads in it. Yippee! It's now the moment of truth. Will this thread on our repair? And will it go? Oh, yes! Go on. That, with a little more leverage, is gonna seat all the way. High five! Next up, degrease, clean, Loctite, thread that fella on tighter than, thread it on tightly. Let's do it. with one yoga hair and one crazy hair for good luck. I don't care if I've got to use the whole pot. I don't want you ever coming undone. Tickles me the right type of way, that does. Oh my goodness, look what we've done to this plate. We put so much torque on it that we have completely bent that half-inch plate that was firmly bolted to the face. I think we can just about say we've got that as tight as it's gonna go. Oh, that's why. It's because we were threading it on so far that this was bowing, coming out proud of it. Great news, apart from the fact that it could be that we haven't threaded it as far as it needs to go because we are now running into a little clearance issue. Technically, that's now an interference issue where the end of that piston rod is now hitting our twisty bit. So what I think I'm gonna do is whack this whole assembly back in the lathe and then face down the end of this rod. It needs to be flush anyway, so that we can hopefully get a little bit more twisting. Obviously, we could make a modification to this, but I know for certain that I do not want this thing to be proud, and so I'm gonna go this route, chuck it in the lathe. But we gotta be quick, because I don't know how long it's gonna be until that Loctite is fully set up. Okay, we just Googled it. Apparently, red Loctite sets in like 10 to 20 minutes. So, oh, for goodness sake, gotta be quick. I'm begging this thing to not twist. Good, that's promising. Good. There wasn't a rush getting it back into the lathe because we had it as torqued, as torquing can properly be torqued, or the Loctite already set. Anyway, I was about to say this component is done. Oh no, can of worms goes deeper, doesn't it? We cannot forget about the most important part. Right here is where we welded. Right there is where we welded. We need locking grub screw tapped and threaded halfway on the shaft, halfway on the piston head. Question is, how on earth are we gonna bloomin' do that? Because that is not gonna fit in the mill without doing some real funky stuff. Not that I'm opposed to doing some funky stuff, but the clock is ever ticking. This hammer's gotta get back together, but it's gotta get back together right. Well, option one, we take a hand drill. The trouble with this is we're trying to drill a hole in the middle of two bits of metal that have different hardness. I think there's a good chance that the drill's gonna go off course, and we also know just how straight I can drill a hole is not very. Option two, we can mount that shaft to the side of my Bridgeport table, here on the side, and twist the head around. Option three, we can twist the head of the Bridgeport 90 degrees sideways, mount the shaft horizontally, drill the hole there. Option four, however, what about a mag drill? Got a new addition to the workshop. It's been very kindly supplied by the guys at Holemaker Technology. A cordless mag drill might do the job. And now for another installment of What Has Alec Received in the Mail? Oh, bloody hell. That's a lot bigger than it looked in the pictures. What? That is a plate-holding lifting clamp. Now that we've got a forklift, got to add to the collection. Good to have some of these fellas in stock. Oh, I know what this is. Wow. Ta-da! One Royal Navy battle ensign added to the workshop. What a delightful gift. Thank you so much. So I did a little bit of research about what it is that we're doing, and it turns out this is called a Dutchman, where we are going to use either a pin, or in our case, a grub screw, to act as a mechanical key, stopping the two things from rotating. And it seems like it's quite a common thing to do, actually. Now, on the original part, I obviously had two of them, each 180 degrees from the other. I've decided that in this case, I'm actually only gonna do one. The reason being, the most important threads in this whole assembly are the threads between the piston rod and the piston head, or the flange. And if I'm putting two Dutchmans in there, I'm going to be doubling the boring away of those threads and the critical friction that they provide. And it means that no matter what, if something bad happens and it comes unthreaded, I have have to do a weld repair to be able to make it functional again. However, if I do just one, it's not like the forces are ever going to be such that it shears a single Dutchman. But two, I've got the opportunity to drill another one in the future if it needs it. Say, for example, with the vibrations, it all of a sudden wants to twist on even more one day. And yeah, that's about that. That's the reasoning I've got. Don't know if that makes sense. Here we go. There we go. The original Dutchman had an M10 thread in it. We're going to do an M12. The fact that this is threaded to M10 here does actually tell you that that was likely a repair as compared to an original feature of the original part. Remember, hammer built in 1915, all the threads are going to be Whitworth threads. If you find something metric, it's not original. On that note, I thought I'd dig out the grub screws that we found rattling around the hammer. Remember, these delightful components too. Oh, actually, this is actually quite funny. So some of you guys in the comments had a suggestion that these bits we found rattling around the hammer may have been something like those. A lifting eye that somebody may have threaded into these holes to install the ram and then turn the machine on without removing it, thus breaking these parts. I was just commenting to myself about the fact that this grub screw didn't at all look like it was the same grub screw as would have been part of the Dutchman, because it's way larger. But what if that grub screw was in fact, threaded into there and was in fact the thread that was the lifting eye that got broken. Great industrial detective work, mystery solved. Back to our Dutchmans. Look at that, you can see the cross-section of the threads. Whoa! On the left-hand side is the mild steel piston head. On the right-hand side is the 7018 weld repair on the piston rod. You can see the thread engagement we've got, and you can see that it's maybe a little bit lacking in some of that weld repair area. Started looking into a different world. Finish it off by hand. Oh yeah. The Dutchman's hole is finished. We're just missing the grub screw. Piston rings time. So, we've got one broken piston ring, and then we've got two differently sized piston rings. Definitely got to replace the broken one. I also want to replace the thin one. Maybe we won't have to replace this correct 6mm piston ring, but I'm going to try and make 3 anyway. So this is what we're going to use. Now that is not just any old bit of steel tubing. No, this is actually very, very special. You see, as we all know now, cast iron is a fabulously lubricitous material, which means for the task that our piston rings need to be up for, it's perfect. See, the piston rings we make are what is actually going to create a seal on the bore of our power hammer. Notice how there is a gap there. Well, when this is sprung in to the bore of our cylinder, like so, that ring is applying pressure on the walls of this bore, and that is allowing it to seal. Making a piston ring isn't as simple as getting a bit of square bar and bending it in a circle. It is an incredibly precise bit of engineering. In its closed state, when made, it needs to be a ring with a diameter that matches the diameter of our bore. Then, once we've made that perfect, we are going to cut it, split it, stretch it open, and heat set it so that when it's then compressed into its final bore diameter, it's applying some outwards pressure. I've done enough research to figure out this is a proper project. Learned a lot from some of the guys on YouTube, like Mr. Crispin, so let's get to it. These are our bore measurements. It's a little bit ovalized. We're going to work to the largest diameter. And as you can see, that is a little bit proud by 0.5 millimeter of the diameter of our piston head. Again, that's because it is the rings that are contacting the bore, hopefully not ever the piston head. Finito. Let's go ahead and print that. There we go, and modern printers. Quick sanity check. It goes, woohoo! Okay. We are 0.4 millimeters away from exactly where we need to be. That's about 15 thousandths of an inch. I'm not going to go any further until we get the inside board to dimension. The theory being, if there's any sort of kind of weird stresses that go different once I bore out the inside, if the dimensions then change, we'll have that margin to skim it back down before we get the tool post grinder on it. So now it's time to make that joke again. That joke that we all know. Frankly, it's getting a bit boring. Now starting to get into accurate measuring territory. 155.145. Almost there. Come on.
Make this the most accurate bore you've ever done, Alec.
157.4. Thousandths of an inch larger than I was hoping. I wanted 157.02, I got 157.04. Maybe we just measure it again. Maybe I gripped it too tight.
Do the hokey pokey.
That's what it's all about. 157.3. I was aiming for 157.02. We are one smidge, technical term for 10 microns, above that. But you'll note that isn't the same number that's on our actual drawing. It's 0.1 millimeters smaller. More on that later. Now change tooling so that we can finish turn the OD. Got to figure out where that tool is though. So, have a look at this. Bring in the tool while we give that a wiggle. When it stops a wiggling, we know where we are. There we go. Cigarette paper is 3 microns. So then simple maths to account for that increase on the radius. Plug it into the DRO. We know where we are. .156.58, perfect.
Le moment de vérité.
Fantastic. 168.52. We're on the money. Look at that, outstanding. Parting tool is in. We're gonna make our first ring. I've allowed 1/1000th of an inch of extra thickness that we can hopefully sand off and make flat. Woohoo! Yeah, baby! That's our first ring. Yes, we're on the money. This should be a little bit too snug in the piston ring groove. Oh, yes! Giving us just a little bit to sand down. 3 more to go. I'm making sure that we have spare, just in case. Just so I can sanity check my allowances, I'm giving it a gentle sand. Make sure it can fit in to the groove as it's meant to. Yeah, I think I've made them a bit too tight. That's gonna take too much sanding time to get down. So we're gonna take a smidge less on the next little slice. Perfection. Here are our 4 rings. These 3 have a perfect width to them. We of course still need to take some material off our thick one though. Hopefully this doesn't take too long. Otherwise we're gonna have to go set up the surface grinder to make this happen. To put into context how much material we need to remove, the material that we have to remove is almost identical to the thickness of cigarette paper. Conceive of that. This is why precision is so exciting, and it's part of why I'm just absolutely having a ball on this project, because we are diving into precision and I'm having to really learn about it. But imagine this, the difference between the type of fit that is correct and the type of fit that is not is 1 cigarette paper. Okay, 6.05. That's what we're aiming for. Yep, perfect. That's the type of fit. Make sure there's no burrs. As delightful as precision is, sometimes one does need a breather. Let's unbox what I bought on eBay. Ooh, yes. Oh, yes. Oh, that is a Carver clamp. Apparently, these are meant to be the bee's knees. A really heavy-duty welder's clamp. Unfortunately, my clamp supply here in the workshop is abysmal. In the Montana workshop, we had a fabulous array of clamps that Jason at Fireball Tools gave us. Here, this is my sorry collection. I have not been investing in the workshop enough over the years, and as much as it hurts the pocketbook, as I think you can tell, I've been investing a little bit more in it over the past few months. Oh, how sweet. We even got a little baby offspring Carver clamp. Thrilling. think I've even got a couple more on the way. How funny is that? Swivel hook so we can make an attachment for the forklift. Ta-da! Looks in decent nick. By the way, if you've got big fat spare clamps, let me know, I might buy them from you. All right, the next step is splitting the rings. It doesn't do the job it's meant to do if it's not split. Let's figure out how to make our cut. Unfortunately, I don't have a slitting saw. That would probably be the better way to get it done, so we're gonna have to see what we can come up with. Jeweler's saw is the thinnest saw I've got in here at 1/3 of a millimeter. Let's see what nonsense we can come up with. Oh, ha! Straight to it with the nonsense. I'm interested to see what's going to happen when we pop through. Is it just going to explode? Is it going to stay where it is? Is it going to pop inwards more? A real adventure. Woo! We're through! Yay! And that's fascinating though, it actually went in more. The blade's 1/3 of a millimeter thick, about 15 thou, but there is no kerf because it is actually snapped in. God, look how flexible it is. I can open it up really easily. Whoa! Don't snap. 3 more to go. There we go. The piston rings have been turned, split, which is great, but they need to be expanded so that they can apply their correct spring pressure in the bore when it's all said and done. Okay, here's the thing. I just got back from Weekend Maker Central. I had a fabulous time meeting some of the viewers of the channel, which is awesome. But while I was there, I had some really interesting conversations about the steam hammer restoration, and I was chatting away, describing the piston rings that I've been making out of cast iron, and what, you making them out of cast iron, Alec? Yeah. You know, like steam engines, steam locomotives, they've all got like cast iron piston rings, lubricity, right? Oh, what? For the hitting piston? Oh no, they're steel. What? Yeah, they're steel. Well, I think of the G-forces on impact, Alec. Cast iron, it just breaks. What? Yeah, it's normal in massy power hammers, like massy clear space power hammers. Yeah, they're all steel piston rings. So yeah, they'll be steel in your hammer. What? You know, it's tough here, guys, right? Because in doing my research on this project, finding out information about a steam power hammer is too niche to be able to get the info. So I'm doing a lot of research as if it's just like a steam locomotive or a steam traction engine. That's the main context through which we're looking at this. And the potential fatal flaw of that is not recognizing the ways that this steam power hammer is different to steam engines. Steam engine piston goes up and down the cylinder, experiencing some G-force at the end of the stroke as it decelerates and then changes directions, but it's nothing like a power hammer. When this ram is traveling up and down 240 times a minute, and it is impacting a bit of steel, decelerating in 0.5 millimeter from quite an incredible rate of speed, it means that all the components inside here, did a little rough calculation, they could be experiencing upwards of 700 Gs, which means that the piston ring within these grooves, even though there's only 0.1 of a millimeter of clearance there, it is decelerating and slamming into one side of that groove wall with an incredible amount of force. And so, when the most knowledgeable person in the world about massy power hammers, John Nicholson, point blank tells me that these are probably steel piston rings, and they probably want to be steel piston rings. And you think about all these other reasons why you might not choose cast iron for a piston ring, start to feel like a bit of a silly Billy. The unfortunate thing is I found this out 36 hours after having made my cast iron piston rings. And so with this new information, my plan of attack is as follows. I need to have a look at our original piston rings. We need to determine were they cast iron or were they not. There is still a chance that these are cast iron, and there is still a chance that it will be fine. If these are cast iron, I can keep moving forwards, because if we got 100 years out of one before one broke, it's gonna make me feel pretty confident to carry on with our cast iron ones. But if it turns out that we can determine the original piston rings were in fact steel, I'm gonna have to start over again. So here's what we've got. Piston ring, key steel, for sure cast iron. Oh, for f***'s sake, that looks like steel. Steel, cast iron, oh, for goodness sake. Do you remember a couple of weeks ago, Jamie, when I'm stood here at the mill saying, in machining, you must never make assumptions.
What's hilarious is that you could have done this test the other day in 5 seconds. Instead, you spent 2 days making piston rings.
I could have done that test 5 weeks ago when we first identified the piston ring problem. That is a colossally expensive mistake. Not that we need any more confirmation, but we can further confirm if this is steel by hardness testing it. Okay, 20 Rockwell C. Cast iron is 0, Rockwell C. Final test, not that we need any more confirmation. Yeah, you see, cast iron would not bend like that before it breaks. Now my freshly turned cast iron ring. Yep. Now imagine if, in a very, very, very hypothetical world, I got so good at making piston rings that I decided that I wanted to start selling my services as a piston ring maker to the world. It would actually be quite simple, because I could head to my Squarespace website, I could add a new product, being the piston rings, I could include the proposed lead time, and I could use the form feature to then have the clients input the data that they need to provide me for me to be able to make them the piston ring size that they need. This is why today's sponsor Squarespace is so powerful, and you can try building yourself a website with Squarespace at squarespace.com/forge. That'll get you a free trial, and code FORGE at checkout will get you 10% off all your purchases. I particularly love Squarespace because you can sell unlimited physical products and digital products. You can sell your time with Squarespace scheduling, and you can run your email marketing campaigns directly within Squarespace. It's incredibly easy to use because they got countless drag and drop themes. I love that Squarespace empowers creatives like you to have a beautiful website that's easy to run and lets you do more of what you love in the workshop. So please, again, go to squarespace.com/forge for a free trial. Code FORGE at checkout gets you 10% off your purchases, and that includes your domains. With that, my new cast iron piston rings are destined for the scrap pile, and I need to find some steel to urgently make the new ones. I've got no idea how the process is going to go with steel. There's not the same volume of published information about it as there is with cast iron. We've got a whole lot to figure out, and I hope it goes swimmingly.